In this session, we continue our discussion on the transportation problem. Transportation problem talks about transporting a single item from a given set of supply points to a given set of destination points. The supply in supply point I is Ai and the requirement in demand point or destination point J is Bj, and the problem is one of finding a least cost transportation from the supply points to the demand points, where Cij is the unit cost of transportation. The problem is formulated as Xij is quantity transported from supply point I to destination point J. The objective function is to minimize the total cost of transportation Cij, Xij, subject to supply constraints. So, for every supply point, total quantity that leaves the point should be less than or equal to what is available. So, Ai is the quantity available in supply point I, and as far as every demand point or destination point is concerned, is greater than or equal to Bj for every j. Xij is greater than or equal to 0. Now, this is a linear programming problem, but we will not be solving this directly using the simplex algorithm. We will see that this problem has some more structure which we will try to exploit and use an algorithm which is a slightly different version of the simplex algorithm. Now, sigma Ai represents the total availability and sigma Bj represents the total requirement. So, if sigma Ai is greater than or equal to sigma Bj, which means the total availability, which is the sum of all these, is more than what is required, then it is possible to transport the entire requirement such that the demand of every destination point is met. If sigma Ai is strictly less than sigma Bj, which means that the total availability is less than the total requirement, then obviously all the requirement cannot be met. So, we right now assume that sigma Ai is greater than or equal to sigma Bj, so that the requirement of all these points are met. The next thing would be, assuming that the total supply is more than the total demand, we will be sending quantities from each of the supply point to one or more of the destination points, so that we meet the demand as well as minimize this transportation cost. It is very reasonable to assume that the transportation cost Cij is greater than or equal to 0 for all Ij. Transportation cost cannot be negative. So, when the transportation cost is non-negative, then we will only end up sending exactly the amount that is required, and none of these destination points will receive even 1 unit more than what it requires, because that extra unit has to be transported from one of these supply points, and that can only increase the cost of transportation. For example, if this requires B1, we will send exactly B1, we will not send B1 plus 1. That extra unit would increase the total cost of transportation if it is strictly greater than 0, or if it is 0, it would still retain. So, in some sense the optimal solution will send exactly the quantity that is needed in each of these destination points. So, we would solve this problem where the greater than equal to inequality has now been converted into an equation. Now, if we consider a very special case where sigma Ai is equal to sigma Bj, then what will happen is we will not only meet the exact requirement of every destination point, but we would also be utilizing all that is available as far as each of the supply points is concerned, which means this inequality also becomes an equation. So, now the transportation problem, under the assumption that sigma Ai is equal to sigma Bj, which means total supply equals total requirement, reduces to the same problem except that the inequalities are all now equations. Now this transportation problem, which has all equations, is called a balanced transportation problem. A balanced problem has equations, and the original problem, the unbalanced problem, which is the original problem, has inequalities. So now we have defined two types of transportation problems. One is called the unbalanced problem, which has inequalities less than or equal to here and a greater than or equal to here, and a balanced problem which has equations which will satisfy the condition sigma ai equal to sigma bj. Now as far as solving the transportation problem is concerned, we will solve the balanced transportation problem. We will show that it is easier and better to solve the balanced problem, and then we will also show a way by which every unbalanced problem can be converted to a balanced problem and then solved. So let us look at solving a transportation problem now. The solution to a transportation problem has two stages. One is called identifying a basic feasible solution, and the second is to get the optimal solution. Now we look at three different ways of identifying a basic feasible solution. One is called the northwest corner rule, minimum cost method, penalty cost method, also called Vogel's approximation method, and we will be looking at two different methods to get to the optimal solution. One is called stepping stone method and the other is called MODI, modified distribution method. Or UV method. So we will be looking at all these five. Now we should remember that these three, northwest corner rule, minimum cost method and Vogel's approximation method, help us get a basic feasible solution, while we can use any one of these to get to the optimal solution after we get an initial basic feasible solution. We should also remember that this is a linear programming problem, but we do not use the simplex algorithm directly. We use an algorithm which has all the properties and characteristics of the simplex, but it is a slightly different version of the simplex algorithm. Normally if we take any linear programming problem, if we take the standard problem that we have looked at, a maximization problem with all less than equal to constraints, then the first basic feasible solution will be very weak with respect to optimality. If we solved a maximization problem with all less than equal to constraint and all greater than or equal to variable, the starting basic feasible solution with all slack variables in the basis gives us an objective function value of 0 for maximization. Even though it is a basic feasible solution, it is not a very good basic feasible solution with respect to the objective function. The very nature of the transportation problem, as we will see, will help us get a very good basic feasible solution rather than arbitrarily or simply starting a solution with slack variables. It is easy and it is possible to get a good basic feasible solution, so that once we concentrate on this and get a good basic feasible solution, the number of iterations to get to the optimal solution reduces. Therefore we follow a separate algorithm where we concentrate on getting a good basic feasible solution, and then apply the optimal algorithm to the basic feasible solution to get to the optimal solution. So, we will first look at each one of these through a numerical example, and then we also explain these two with a numerical example. Now, before that we also represent the transportation problem in a very convenient form. We do not normally represent it this way, we represent a transportation problem in a very convenient form which we show here. This 3-row 4-column matrix represents a transportation problem with 3 supply points and 4 destination points. The supplies in these 3 points are 40, 60 and 50. The requirements or the demand in the 4 points are 20, 30, 50 and 50. So, these are the AIs, A1, A2, A3, the supplies. These are the BJs, B1, B2, B3 and B4. The total supply is 150 and the total demand is also 150. Therefore, this is a balanced transportation problem. The unit cost of transportation from I to j, Cij, is written as follows. You have 4, 6, 8, 8, 6, 8, 6, 7, 5, 7, 6, 8. It is customary to write the unit transportation cost in the top left hand corner of the individual allocation in a smaller size, so that it represents the transportation cost. Now, this in total represents a transportation problem with 3 supply points with supply 40, 60, 50, 4 destination points or demand points with 20, 30, 50 and 50 respectively, balanced indicated by the total, and unit transportation costs are given here. Now, let us try to get a good basic feasible solution to this problem. Remember, we are going to look at 3 methods: northwest corner rule, minimum cost method and the penalty cost or Vogel's approximation. First, let us look at the northwest corner rule to solve this. Now, given the transportation matrix, first look at the northwest corner or top left hand corner. So, this is the northwest corner or top left hand corner. Now, as far as this allocation is concerned, there is a supply of 40, there is a requirement of 20. So, try to put as much as possible into this. So, 40 can go in, only 20 is required. So, take the minimum and allocate 20 here. So, from the first supply point to the first requirement point, we have allocated 20. Now, we have met the requirement of this 20. So, just put a dash indicating that this has been met, and because 20 has been allocated out of this 40, now 40 becomes 20, a balance 20 is available. Now, once again go to the top left hand corner or the northwest corner. Now, this is the top left hand or the northwest corner. Now, the supply is 20, requirement is 30. So, only 20 can be put here, put the minimum. Now, this 20 is exhausted. So, put a line indicating that this supply is exhausted, and this 30 now requires a further demand of 10 because 20 has been supplied. Now, go back and identify the northwest corner or top left hand corner, which is this corner. There is a supply of 60, there is a requirement of 10, so you can meet only 10. Now, this 10 is exhausted, so this is over. So, this 60 becomes 50. Now, once again go to the top left hand corner, you get this is the top left hand corner. There is a supply of 50, there is a requirement of 50, so you can meet the 50 here. Both these are exhausted. Now, once again there is only one point available, which is the northwest corner. Once again supply 50, requirement 50, so 50 is allocated. So, all the supplies and demands are met, and we have got a basic feasible solution with this. In fact, as far as the matrix is concerned, even though we clearly said the supplies are 40, 60, 50 and demands are 20, 30, 50, 50, even interchanging the supply and demand will not change anything because it is a balanced problem. However, as far as this problem is concerned, we would represent supplies here on the right hand side and the demands here below the transportation matrix. Now this is a basic feasible solution. We will later define what exactly is a basic feasible solution to a transportation problem. At least this is a feasible solution because this solution meets all the supply demand constraints and has all allocations greater than or equal to 0. This is feasible because it satisfies all the constraints. Now the cost associated with this allocation, for example, this solution says allocate 20 from the first supply to meet the demand, first demand. As far as the second demand is concerned, allocate 20 from the first, 10 from the second. As far as the third demand is concerned, allocate 50 from the second, and as far as the fourth demand is concerned, allocate 50 from the third. So all the 40 is allocated, 60 is allocated, 50 is allocated, and all demands are met. So the cost of transportation would be 4 into 20, 80, plus 6 into 20, 120, plus 8 into 10, 80, plus 6 into 50, 300, plus 8 into 50, 400. So this is 280 plus 5, 700 equal to 980. So we have a starting solution using the northwest corner rule, which has an objective function value of 980. So we will just note it down here, northwest corner rule has objective function value of 980, and that is shown in this example. The same allocation that we have here is shown here. See, the 40, 60 and 50 are the supplies, 20, 30, 50 and 50 are the requirements, 20, 20, 10, 50 and 50 are the allocations for a total of 980. So this is one of the ways of getting a basic feasible solution to the problem. Now let us look at the second method, which is called the minimum cost method, to get this. So we represent the problem again and we start the allocation using the minimum cost method. Now what is the minimum cost cell or minimum cost ij that we have? That is 4 and it happens to be for this particular position. Now identify that position which has the minimum cost. So we identify this. Now the supply is 40, the requirement is 20, so allocate 20, the minimum of possible supply and possible demand. So this is exhausted and this 40 becomes 20. Now look at the remaining minimum cost. Now we have minimum cost of 6 here, 6 here and 6 here. So there is a tie between this, this and this for the minimum cost position. So we can break the tie arbitrarily to choose between this, this and this. Let us assume that we pick up this 6 arbitrarily. So this would mean that there is a supply of 60 and a requirement of 50. So you allocate 50 here, this is over and this becomes 10. Now once again look at the minimum cost. Minimum cost is unique, it is at this 6. Now as far as this 6 is concerned, there is a supply of 20, there is a requirement of 30. So allocate 20, this is exhausted Now this becomes 10. Now the minimum cost is either here or here. Once again we can break the tie arbitrarily and we choose to allocate this position. So as far as this position is concerned, there is a supply of 50, there is a requirement of 10, so allocate 10 here. This is over, this goes, this 50 becomes 40. Now once again the minimum cost position is here, supply 10, requirement 50, allocate 10, this gets exhausted, this becomes 40. Now this is the only one that is available, supply 40, requirement 40, allocate 40, this goes, this goes. Now this is another basic feasible solution. Once again we have not yet defined what a basic feasible solution is, but it is a feasible solution where all the supply demand constraints are satisfied, all allocations xij are greater than or equal to 0. Let us find out the cost associated with this solution, which is 4 into 20 80 plus 6 into 20 120 plus 6 into 50 300 plus 7 into 10 70 plus 7 into 10 70 plus 8 into 40 320, 200 500 570 640 960. So the minimum cost method gives us a solution with 960 for us. Now between the Vogel's method, between the northwest corner rule and the minimum cost method, we realize for this example minimum cost is able to give a slightly lesser objective function value compared to the northwest corner rule. The problem being a minimization problem, we would be interested in this solution when compared to this solution. There is also one slight difference between this and the previous one. If you could go back to the northwest corner rule. Now the only difference that we have is we have 6 allocations in this, in the minimum cost solution, whereas we have 5 allocations in the northwest corner solution. For example, there is a 20 here, there is another 20, 10, 50 and 50. There are 5 allocations here while there are 6 allocations here. But then when compared to the cost, this has a lesser cost than the northwest corner rule. This is understandable because the method is based on progressively identifying least cost positions, whereas in the northwest corner we did not consider the cost while making the allocation. So any method which considers cost while making the allocation is expected to perform better than the one which does not consider cost, and it is only obvious that in this case minimum cost has given a less cost than the northwest corner solution. Now let us look at a third method which we will use to find out a starting solution to the transportation problem, and let us do this. Now let us look at the first row. Now this 40, because we want to minimize the objective function, we would ideally like to put as much out of this 40 as possible to this because it has the least cost. Now if we are not able to allocate some or all of this 40 to the least cost position, then there will be an additional cost or penalty associated with that. There will be an increase in the objective function because we are not able to allocate to the least cost. So the penalty that we will incur per unit for not being able to put in the least cost position is the difference between the least and the next least. So there will be a penalty of 2 associated with this row. If I am not able to allocate here, then definitely my cost will increase by 2 for every unit that is allocated, because I may do it here. So the minimum penalty that we will incur by not allocating in the least cost position is the difference between the minimum and the next minimum, or the next minimum and the minimum, which is 2, 6 minus 4, 2. As far as this is concerned, the penalty will be 0, because there are 2 positions with the same minimum cost. So if I am not able to allocate here, then there is a chance that I might still do it here, so my penalty is 0. As far as this is concerned, the penalty is 1, minimum is 5, next minimum is 6, so penalty is 1. As far as this column is concerned, I would ideally like to get everything from this because of this 4, but if I do not, then I will incur a minimum penalty of 5 minus 4, 1 at least for every unit. Similarly, here the penalty is 7 minus 6, which is 1, 6 minus 6, 0 in this case, and 7 minus 8, any of these 8 minus 7 is 1. Mathematically, we can define the penalty as the difference between the second smallest number and the smallest number. Physically, the penalty, this index represents the minimum additional cost per unit that we will incur by not being able to allocate to the least cost position, if it is a supply, and not getting it from the corresponding least cost if it is a demand. So we compute all these penalties. Now we look at these penalties and find out the maximum penalty. The reason is, now this is more important compared to the rest of them, because here by not allocating into the least cost, I am incurring maximum penalty as far as all the penalties are concerned. So I will look at the row or column that has the maximum penalty, which is this. And what does this mean? Now having identified that this is the most important row because the penalty is very high, when considering all the rows and all the columns, so the first decision will be made on this row, because this row has the highest penalty. And now in this row I will try to put as much as possible in the least cost position, because by not putting it in the least cost position I will incur this much penalty. So the algorithm is compute the penalties and then find out that row or column that has maximum penalty, and having identified that row or column, try to put as much as you can in the least cost position. So I look at this, this is the least cost position. So this supply 40, demand 20, I put 20. Now when I do that, I have exhausted this 20, this 40 becomes 20. Now I have to compute the penalties once again. Now as far as this row is concerned, minimum now is 6, next minimum is either of these 8, so the penalty is 2. As far as this row is concerned, minimum is 6, next minimum is 7, so penalty becomes 1. Here the minimum is 6, next 7, penalty is 1. Column penalties will not change and they remain as they are. So now once again this has the maximum penalty, therefore go to this row and try to put as much as you can in the minimum position. So the minimum position is here. Now supply is 20, requirement is 30, so put 20, this gets exhausted, this becomes 10. Now compute the penalties again. For this row, the minimum is 6, next minimum is 7, this is 1, minimum is 6, next minimum is 7, this is 1. In fact, the row penalties will not change. And now go back and look at the column penalties. This is minimum 7, next minimum 8, this penalty is 1, 6 and 6 will give a penalty of 0, 8 and 7 will give a penalty of 1. So now the maximum penalty is 1, 1, 1 and 1 here. There is a tie for the maximum penalty and the tie can be broken arbitrarily, and right now we try to look at this one and break the tie. So when we consider this column for breaking the tie, the minimum position is this. Now try to put the maximum, so you get 10 here, this is exhausted, this goes and this becomes 40. Now once again compute the penalties. 7 minus 6 1, 8 minus 6 2, 6 minus 6 0, 8 minus 7 1. Maximum penalty is here. So this is the minimum position. So try to put the maximum here 40, this 40 goes, this is exhausted, this becomes 10. Now there is only 1, so 6 minus 7 1. So look at the minimum position, there is a 10 and a 60 here, so put 10, there is a remaining 50 and put this 50 here. So you get this solution from the penalty cost method or the Vogel's approximation method. Now this also has 6 allocations like that of the minimum cost, and let us find out the cost associated with this. So 80, 4 into 20 80, plus 6 into 20 120, plus 6 into 10 60, plus 7 into 50 is 350, plus 7 into 10 70, plus 6 into 40 is 240. So 200, 260, 310, 610, plus 70, 680, plus 47, 20, plus 200, 920. So this penalty cost, also called Vogel's approximation method, VAM for short, now gives us a basic feasible solution again with objective function value 920. Now there are two aspects to it. Number one is this Vogel's approximation method is expected to perform slightly better than the minimum cost, because not only does it do a minimum cost allocation when it comes to the after identifying the row or column, but it also uses more information considering the penalties. So it goes into one more level of detail in carefully choosing the row or column to be considered. Therefore it is expected to perform slightly better than the minimum cost method, and it happened in this case where it gave a solution that is slightly better than that using the minimum cost method. Now there are two other dimensions. One is we did have at one point in time we had tie in 4 positions 1, 2, 3 and 4, and then we broke the tie arbitrarily by considering this. If for example we had considered some other position to break the tie, then we may end up getting a slightly different solution for the Vogel's approximation method or for the minimum cost method as well. Even here we could get a tie. When we look for the least cost entry, we could get a tie. Similarly with the Vogel's, the tie is, the possibility of a tie is more because we are computing the penalties. So wherever we have a tie and we break the tie arbitrarily, depending on the choice, which is an arbitrary choice, the solution will change, the allocations will change, as well as the costs would change. If we are lucky, we could get something which is much lower. If you are not really lucky, then you would get something with a slightly higher value compared to this. For example, we can go back and show one more solution as to what will happen when the tie is broken arbitrarily in the penalty cost method, which we will do now. Four, 6, 8, 8, 6, 8, 6, 7 and 5, 7, 6, 8. Let us quickly compute the penalties. So penalty is 6 minus 4 2, 6 minus 6 0, 5 minus 6 1, 5 minus 4 1, 7 minus 6 1, 6 minus 6 0, 7 minus 8 1. This has maximum penalty. So choose this row, this is the minimum cost position, 40 available, 20 required, put 20, this goes, this becomes 20. Penalty is 6 minus 8, 2, 7 minus 6, 1, 7 minus 6, 1, 8 minus 7, 1, 6 minus 6, 0 and 1. Once again this is maximum penalty. Identify the minimum cost position, 20 supply, 30 requirement, 20, this goes, this becomes 10. Compute the penalties again, 7 minus 6, 1, 7 minus 6, 1, 8 minus 7, 1, 6 minus 6, 0, 8 minus 7, 1. Now there is a tie between these 4 positions. Last time we took this one, this time let us take this one. So if we break this tie arbitrarily, this is the least cost position, 60 and 50, so I put 50 here, so this goes, this becomes 10. Now once again find out the penalties, 8 minus 7, 1, 8 minus 7, 1, 8 minus 7, 1, 8 minus 7, 1, we could choose any one of these. For example, if we choose this, so I get 50, if I choose this one, then this becomes the minimum cost position. So I get a supply of 50, requirement of 10, so I put a 10 here, this goes, 50 becomes 40. Now we have only 2 positions, I have 10 and a 40, so this 10 will go here, this 40 will go here. Cost associated will be 20 into 480 plus 120 plus 300 plus 70 plus 70 plus 320. So 200, 500, 570, 640 plus 320 is 960. So we could have got a solution with 960. So a different tie breaking rule can give a different solution. For example, if we had got this solution, then we realize for this example it is given the same solution as that of the minimum cost. There is absolutely no guarantee that all the time this will be lesser and so on. After all 3 are basically non-optimal. They do not guarantee the best solution at all. They are approximate. They do not, even though particularly the minimum cost and the penalty use cost information in getting the solution, they are not optimal. They only provide us with a basic feasible solution. The reason is, towards the end of the allocation, you would realize that you normally do not have a choice. For example, when we went through the same calculation, somewhere when we allocated this 50 here, for example, when we had a supply of 60 and a requirement of 50, we put a 50 here and then we closed this and we brought it to 10. Now the last 2 allocations we do not have any control. Automatically a 10 comes here and a 40 would come here. So towards the end of all the methods, we actually do not make a decision. We identify the place to allocate at the very early stage of the allocation, and towards the end we realize we actually do not have a choice and we are forced to put it in certain positions. And simply because of this, they do not guarantee any optimality. Sometimes they can be very high. For example, if this had been say 20 instead of 8, then this value would be very, very high. So we do not really have a choice with respect to the last allocations, and therefore all the 3 methods are heuristic and non-optimal in nature. They only provide a starting basic feasible solution to the transportation problem. All these 3, we have to keep in mind that all 3 do not provide the optimal solution. All these are not optimal solutions to the transportation problem. They only provide us with a starting basic feasible solution, which is a good solution. For example, we would be happy to start with a solution with cost 920 and then optimize the cost further, rather than starting with a solution which has a much higher cost than 920. So we have seen 3 methods to get the starting basic feasible solution to the transportation problem, and we saw we had 5 allocations here, we had 6 allocations here. In this solution we had 6 allocations, but once again in here we do have 6 allocations in this. So let us try to understand what is a basic feasible solution to the transportation problem. All these are feasible solutions, but let us try to understand what is a basic feasible solution to a transportation problem next, and then we will try to solve the problem optimally using any one of these 3 as a starting solution, and then also see how to solve the problem for any given starting solution. Right. Next. Now, what is a basic feasible solution to a transportation problem? A basic feasible solution satisfies the following conditions: the row and column constraints are satisfied, the non-negativity are satisfied, the allocations are independent and do not form a loop, we have to see what this is, and there are exactly m plus n minus 1 allocations. Now, all the 3, if we go back and observe, all the 3 satisfied the first 2 out of the 4 conditions. We have to see whether all of them have a loop or do not have a loop. They had certainly different allocations. For example, this had 5, the rest of them had 6. Now, what is m plus n minus 1? There are m supply points, there are n demand points. So, there are 3 supply points and 4 demand points, m plus n minus 1 is 6. So, all these had 6 allocations, this had less than that 5. So, in some sense all of them satisfied m plus n minus 1, this did not, but these 2. None of them exceeded m plus n minus 1, they had m plus n minus 1 or less. Now, let us look at the third condition and first understand what this loop is, and then go back and see whether this satisfies the loop condition or does not satisfy the loop condition. For example, if this satisfies the loop condition, then this is basic feasible. Right now this is feasible because it satisfies all the supply demand conditions, it has satisfies the non-negativity condition, it has exactly m plus n minus 1 allocations. So, the only thing we have to check whether it satisfies the third condition. So, let us first understand what this loop is. To explain the loop, let us consider the problem that is shown here. We have the same problem with 40, 60 and 50 supply points that we have here, same requirements 20, 30, 50 and 50 that are shown here, same cost structure, but we show a different allocation. So, we now have a problem with 7 allocations, 10 here, 30, 10, 50, 10, 30 and 10. Now, let us look at these 7. Now, these also satisfy the supply demand requirement, they also satisfy the non-negativity requirement, but then we observe something additional in this. If we start with the top corner 10 and then we observe something like this, starting from this 10 top corner, we can draw this line that goes to this 10 and then we move horizontally to get into this 10, we move vertically to go to this 30 and then we move horizontally to come back to this 10. This is called a loop. So, given a solution starting from one of the allocations, if you are able to move horizontally and vertically, move across allocations and you are able to come back to the starting point, then this represents a loop, and loop is some kind of a dependence in the solution, which shows that these 7 are not independent allocations. There is a dependency here and that dependency is given by this loop. So, if the solution has a loop, then we should break the loop and make it independent. Now, what we do here is this, we try from this 10, we try to put a minus 1 here and see, we try to bring down this 10 to 9 by looking at by putting a minus 1. Now, this minus 1 would mean that we have to satisfy this 20, so this 10 becomes 11, and because we have added a 1 here, this 10 would become 9, we end up subtracting, and then because we have subtracted here, this 30 would become 31 and we added here. So, the net is 0. In a loop we should get a net equal to 0. Now, what is the effect of this change? Reducing one of the elements of the loop by 1 would now reduce the cost by 4, cost reduces by 4 here, which is shown as a minus 4 here, cost increases by 8 here, which is shown as a plus 8, cost reduces, this minus 1 will reduce the cost here, which is minus 8, and cost increases here, plus 1 increases the cost by 5. So, the net change in cost is equal to plus 1. So, the effect of reducing this 10 to 9 would actually end up increasing the cost by 1. So, now what we need to do is, if we had increased this 9, the 10 that was originally here to 11, and by the same loop this 11 would have brought this to 29, this to 11 and this to 9, then we would have a net change of minus 1. For example, if we had done this, then we would have a net change of minus 1. Now, this is desirable. So, what do we understand? This is desirable because there is a reduction in the cost associated with this. Being a minimization problem, we would consider this to be desirable. Now, every loop can be broken in two ways, one of which would give us a positive net increase and the other would give us a negative net increase. Now, this is desirable, so we would consider this. So, it is now desirable to break the loop by adding to this position and not by subtracting to this position. Now, now we realize that every addition here would reduce the value by 1. So, we want to add as much as we can here, and that is given by this. For example, the maximum we could, if we keep on adding here, if we make this as 12, then this will become 8, 13 would make this 7 and so on till this becomes 20 and the other one becomes 0. Go to the previous one. So, since till this would be made 20 and this would be made 0. So, if we make this 20, then this would change to 20, this would change and this would become 0, and that is shown in the next table. 20, 20, 20, 10, 50, 30, this 20 will become 0. This is not 20, this would become 0 because of that change. Now, we have 1, 2, 3, 4, 5, 6 positions excluding this. We have 6 positions and we have exactly m plus n minus 1 allocations. So, a loop should have, breaking the loop should give us exactly m plus n minus 1 allocations. Now, let us move to another example. A loop can be broken in two ways, one of which will result in a solution with less cost. It is advisable to break the loop as we did and obtain a better solution with a lesser cost. When a feasible solution has more than m plus n minus 1 allocations, as we had here with 7, then it automatically tells us that there is a loop somewhere and that loop has to be broken. When we have more than m plus n minus 1 allocations, we can be confident that there exists a loop. The solution is not basic feasible, we have to break the loop and then make it basic feasible. We also observe that the 3 methods, northwest corner rule, minimum cost and Vogel's, will not give more than m plus n minus 1. The reason being, whenever we made an allocation, we allocated the maximum possible, which is the minimum of the supply, net supply and the net requirement. By allocating the maximum possible, which is the minimum of the two, we make sure that we will not have a loop. Therefore, these 3 methods are acceptable, these 3 methods are desirable simply because they do not give a solution with the loop, they give basic feasible solutions. Now, they do not give more than m plus n minus 1, they allocate, since they allocate maximum possible every time, they will not have solutions with the loops. Next. Now, we need to look at one more aspect which is given by this example. Once again, for the same supply and requirement of 40, 60 and 50, 20, 30, 50 and 50 and the same cost structure that we have, we provide here another solution. We provide another solution with exactly 6 allocations, m plus n minus 1 is 6, we provide a solution with exactly 6 allocations. Now, the row column constraints are satisfied, 10 plus 30 is 40, 10 plus 30 plus 20 is 60, 50 comes here, column additions are also satisfied. There are exactly 6 allocations, but if we look at these allocations very carefully, we realize that there is a loop. So, on one hand, when we know that If we have more than m plus n minus 1, there is definitely a loop. When we have exactly m plus n minus 1, it does not guarantee that we do not have a loop. We could have a hidden loop as we see in this. So, when we have a solution that is obtained by any method other than these three, or any method that does not guarantee a loop, then we do not have to look at loops. For example, if we had used any of these three or any other method which would guarantee a non-loop solution, then if we have a solution with m plus n minus 1, we can be confident that it does not have a loop. Now, we do not know how we got this solution, but this solution is feasible, it satisfies the row column and it has exactly m plus n minus 1, but we need to check whether this has a loop, because we do not know whether this was obtained using any of these three or any method which does not guarantee a loop. So, we verify and we realize that there is a loop here. 10, 30, 20, 10 is another loop. So, we follow the same procedure as we did previously. We add a plus 1 in one position and then we break the loop. Finally, after we put the maximum, after we identify the desirable and then we allocate the maximum, we break the loop and we get now 5 allocations here. Now, these 5 allocations are independent, they do not form a loop, but this is basic feasible because it does not have a loop, but it has fewer than m plus n minus 1 allocations. M plus n minus 1 is 6, but it has 5. Now, this is very similar to the northwest corner solution, which also did not have a loop, but had 5 allocations as against the m plus n minus 1 equal to 6. So, when we have a feasible solution with no loop and with less than m plus n minus 1, then it is a degenerate basic feasible solution. Now, this basic feasible solution is degenerate because there is a hidden 6th allocation which is not shown here, which has a 0. So, this is a case where an allocation has a 0, an allocation corresponds to a basic variable and it has 0. So, this is a degenerate basic feasible solution. Next. It also means that 6th allocation should be such that it should not form a loop. It is very important that we have to identify the 6th position and we have to make sure that the 6th position does not create a loop, because we do not want a loop. For example, we cannot identify this position as the 6th because this would form a loop. So, we would not want to do that. So, we can identify any position. We could identify x13 or x23 or x31 or x32 or x34 equal to 0. We should not look at 21. 21 would give a loop. So, we could put an epsilon, the small epsilon indicates that it is a degenerate basic feasible solution, and this epsilon can be put in any position such that it does not form a loop. So, every degenerate basic feasible solution will have an epsilon, and that epsilon is the 6th or the m plus n minus 1th allocation in this case. Now, this kind of brings us to the discussion on getting a basic feasible solution to the transportation problem. So, what have we seen? In a nutshell, we have seen 3 methods to get a starting solution. Now, all these 3 starting solutions are basic feasible. They are basic feasible because they satisfy the supply demand requirements, they have all xij's greater than or equal to 0, they do not have a loop. These 3 will not have a loop because of the way the allocations are made. So, whenever we allocated, we tried to put the maximum, which is the minimum of the supply demand, and because we put the maximum in that position, there will not be any loop with solutions of these 3. So, in order to get basic feasible solutions, we have to guarantee that these the rule or the method that we use to get our basic feasible solution should not give us a loop, as it happened in these 3. A basic feasible solution is also characterized by m plus n minus 1 independent allocations. Sometimes we could get a basic feasible solution out of these 3 with less than m plus n minus 1. Now, that means we have a degenerate solution. A degenerate basic feasible solution has fewer than m plus n minus 1. It satisfies all the supply demand conditions, it does not have a loop. So, whenever we have a degenerate basic feasible solution, it is necessary for us to introduce an epsilon in such a way that it does not form a loop. Now, these three are commonly used methods to get starting solutions, commonly used methods to get basic feasible solutions, and they do not have solutions with loop, and they are desirable. It is not always necessary to use only these three. We could, for example, have arbitrary starting solutions, created using different algorithms and different methods, and we could use them also as starting solutions, but the only thing we have to ensure is that any solution that we use as a starting solution to the transportation problem is basic feasible. If the starting solution is obtained using any of these three, and it is very customary to use the Vogel's approximation method to begin, or the minimum cost method, it is very customary to use one of these, then we are sure that we do not have a loop. So, we will have basic feasible solutions which will have exactly m plus n minus 1 or maybe degenerate. If the solution is obtained by any other method other than these three, or by any arbitrary method, then the first thing we need to do is to check the number of allocations. If the number of allocations exceeds m plus n minus 1, then there is definitely a loop, and that loop has to be broken. And even if the total allocation is exactly m plus n minus 1, we still need to check whether there is a hidden loop, and by breaking that loop we will end up with lesser than m plus n minus 1 and a degenerate. So, the important catch is to be able to get a basic feasible solution to the transportation problem, which is preferably non-degenerate. So, these methods are commonly used to get those basic feasible solutions. Sometimes we may get degenerate solutions also out of this. If we get a non-degenerate basic feasible solution with exactly m plus n minus 1 allocation, it is extremely desirable. If we get a degenerate basic feasible solution with less than m plus n minus 1, then we need to add an epsilon suitably to make it basic feasible and start. So, the first part of solving the transportation problem is to try and get a starting basic feasible solution, preferably using the minimum cost or the Vogel's approximation. The advantage of using these methods are they provide basic feasible solutions, they do not give loop. They may give a degenerate basic feasible solution, but if we get one, we have to accept it. If we are using any method other than these, any method about which we are not confident of its ability to give a non-loop solution, then we need to verify whether the given solution has a loop or not. If it has a loop, then that loop has to be broken to get a basic feasible solution. A basic feasible solution to the transportation problem is characterized by satisfying the supply demand restrictions, satisfying the non-negativity restriction, having m plus n minus 1 independent allocations, and not having a loop. So, we know that these two methods would give us a solution which satisfies all these and is basic feasible. Next thing we need to do is to try and get to the optimal solution from these, either using the stepping stone method or the modified distribution method, and we will see that in the next lecture.